Welcome back to Deep Learning video lecture series, and in this lecture we are going to discuss activation functions. So here I am going to cover mainly we need to understand why activation functions are needed in deep learning, and then key roles of activation function and types of activation functions, and then the last one is the very important point, choosing the right activation function. So let us understand why we need this activation function. So if you remember how a perceptron in a neural network, artificial neural network, or artificial neuron performs, it calculates the weighted sum of its inputs and then add bias. Then it decides whether it should be activated or not. So in this case, like as we discussed, if you look at this basic building block of its artificial neuron, so has inputs and a term bias, and this is aggregated and that will be passed to this non-linear activation function, linear activation function, and the output. So in this case, like it simply calculates weighted sum of inputs and then adds the bias, that is sigma I equal to 1 to n if there are n inputs, and then the weights and biases, that means weighted sum of inputs wi and the bias term bias and this, and then it would be passed to the non-linear activation function. So then it decides whether it should be activated or not. So here the output, that is y hat, can have the values, that is minus infinity to plus infinity. But what values need to be produced? That is the boundary. How do we decide the boundary? Because artificial neuron does not know what are the boundary values, what values need to be produced, what is the boundary values. So to control this output, that is to produce the set of values, so we need an activation function, that is like how to decide which neuron should be activated and which is not activated. And to decide that, so we need a function, that is the purpose of introducing this activation function in deep learning. And if you look at the key roles of activation functions, mainly it introduces the non-linearity. So activation functions are used to introduce the non-linearity. It helps the network to learn, so that is the non-linear activation functions helps the neural networks to understand the complex mappings. And next one is enable deep learning. That means we can stack multiple layers. So that is stacking multiple layers is effective only when activation functions introduce the complexity. That means if you take a linear activation function, so let us take a linear function and there are many layers are stacked like this. So each layer or each neuron in each layer, like suppose in this layer we have two neurons. So we are using this linear activation function. So then weighted sum of the inputs and the bias term would be added and then passed to this linear activation function. Same, like all neurons are having the linear activation function. So then this will be passed this like this. The information is propagated from this layer all the way up to this layer. So whatever in this case, because it is a linear activation function, instead of using, even if you use a single layer and if you use multiple, that is stacking multiple layers also, there is no much difference. So that means the single layer will be enough to represent this entire. So there is no complex this means this linear function will not enable this network to learn the complex patterns. Next one is a control neuron firing. Like decide which neurons get activated, that helping the hierarchical feature learning. So that will also be controlled with the activation functions. And the types of activation functions, like depends on the problem you are going to solve. Like suppose if you want to address a problem that is required only the output either 0 or 1, yes or no, like binary output required. And some problems like if you take a classification problem, so there will be like n number of classes in that, so we need a n number of outputs. So like depends on the problem, so we will select a particular activation function, and we also use the combination of activation functions. So let us quickly go through the 4 popular activation functions, and the many other activation functions were also there, but we are not going to discuss in detail all those functions. So the first function they used in the deep learning, that is neural networks, is a step function, and this is also called as a threshold function. So it produces output either 0 or 1. So only it's a binary output. So here in the graph you can see the values are produced, that is either this extreme or this extreme values. Only the either 0 or 1 produced. Okay. So this is only for binary classification. And next another function, that is a sigmoid activation function. And this sigmoid activation function, that is f of x equal to 1 over 1 plus e to power minus x. So here, and the line from this plot you can observe, it is a smooth and it looks like a step function little. And if you observe, like suppose if you take this point 2.5 minus x value 2.5 and then plus 2.5, how this curve looks like, that means slope, the rate of change. Like suppose let us take and this data point, and what is the slope? So here, and this is delta x, that is the rate of change in x, and this is delta y. And if you take this data point and this data point, and here the rate of change in x is very small, that is delta x is very small, and delta y is huge. That means for small value of x in this region, okay, and this is the region we are observing here. So in this region, for small value of x, the corresponding value, that is a significant, so more large number of value y. That means small change in x, significantly more change in y. Okay, that's why we can observe the steepness in this curve. So here, that means how it is correlated mainly in the deep learning, that is how it is going to contribute sigmoid function while training the deep learning models. So here you can see the gradient is changing, right? And if you take this a tangent and how it is changing, so that is going to affect. And if you look at this outside this region and this part and also this part, here you can see it's a very small change and then it is reaching 1, and similarly here and up to this there's very small change and then it is almost equal to 0. So that means a small change means that is gradient. So the slow learning rate, that we will discuss how the learning rate is correlated, that I will show these plots also to understand in detail. So this here up to this, the learning rate is very slow learning, the gradient very small, and now it is almost equal to 0. There is no change, so it becomes constant, there is no change. So that means if there is no change the gradient, So there will be no update. Okay, so there will be no update. So if there is no update in the weights or biases, and then the model would be expected to perform like in the previous iteration. So no change of no learning happens. So then, so that is a problem here. So that means the gradient becomes vanish. That is a vanishing gradient. That means that becomes very small. The gradient becomes a small. So that is a major disadvantage with the sigmoid activation function. Okay, and another thing is the set of values produced by the sigmoid activation function, that is 0 to within the range 0 to 1. So that means the probability, we know that the probability values are always within the 0 and 1, and the total probability would always equal to 1. So and if any problem which require the output in terms of the probability, like suppose if there are 10 classes, 10 different classes, and if you want to find out whether a particular data point belongs to a particular class or not, and then we'll calculate the probability. Like suppose there are 10 classes, then we'll calculate the probability like this particular data point belongs to class 1. What is the probability? And similarly to the remaining classes. So where the probability is more, that means the category of classes, and then we'll decide that data point would belongs to that particular class. So that kind of probability would be used this sigmoid activation function. And if you look at the limitations that we already discussed, one is a vanishing gradient, and computationally expensive due to the exponential function. That is another disadvantage. So we have this exponential function, so that would be a computationally expensive, because in the real world there will be many number of layers are stacked, and many inputs will be there, many parameters need to be tuned. Next type of activation function is a tanh, hyperbolic tangent function. And you can see the function f of x, so that is equal to e to the power minus x, e2 minus x over ex plus e2 minus x. So now if you observe the set of values, or the values which are ranges from -1 to +1, you can see here, and this is the next range. Now here also you can observe here, from this the gradient becomes constant, becomes 0, and here also there is no change, means the gradient becomes constant, and the gradient becomes vanishes. So then there will be no learning happens. So that would be considered as another, that is again like a sigmoid activation function, one disadvantage. Okay, so and when we compare with the sigmoid activation function, this tanh, the limitations, this is a boundary, whereas a sigmoid activation function 0 to 1. Okay, whereas the tanh has the range -1 to +1. Another very important activation function is a ReLU, rectified linear unit. And here you can see the positive part of this x in this graph, and this one looks like a linear function. In the negative side, it is almost equal to 0. So here there is no limit, that means 0 to infinity it produces. Okay, and the major advantage with this ReLU, rectified linear unit, is the 50% of neurons will produce the output to 0. So then that network becomes the sparse. So sparse. So the accuracy, because it will not be a more complex, like whereas the sigmoid activation function or some other functions, and almost all neurons get activated, then that becomes dense, and that's why it's a computationally expensive. But there is no such like in the rectified linear unit. Only the approximately. Suppose if you assign the random weights, and then there will be maximum 50% of neurons get activated. Next, another very important function is a softmax, and this softmax has 0 to 1. Yeah, so 0 to 1, and this is the equation. So these are the types of activation functions. And one important thing is, how do we select the right activation function? So what are the parameters need to be considered? So here, and based on, we are going to compare this activation function, mainly the type of problem you are going to address. There is no like a fixed like a steps or rules to identify like the right activation function. So that depends on the type of problem you are going to address. So here, if you compare all these activation functions, like the step function, that is a binary or a threshold function, has the range 0, 1, and it's not a differentiable. Okay, like suppose f of x equal to some c dot x, and it becomes, gradient becomes constant here. Gradient becomes so constant. So there is no change in this. Like suppose if you take this one, so the gradient is constant. Next, the key issue is a no gradient because it's constant. And best use case, perceptrons, this step function, the perceptrons with the step functions were used long back, early. And next one is a sigmoid activation function, 0 to 1, that is a small for the large x value. And the problem is vanishing gradient, as we discussed, and it is mainly suitable for the binary classification. Next, tan h, it has the range -1 to +1, and this is a small for the large x, and it also suffers from the vanishing gradient problem. And mainly the hidden layers, it is more suitable to use in a hidden layers as activation function. And next, ReLU, rectified linear unit, it has the range 0 to infinity, outbounds, and there's a problem in this ReLU, that is dying neurons. That means the gradient becomes a 0, so there's no change. So then the neurons will die. So it is mainly recommended to use in the deep, that is hidden layers. Next, softmax, it has the range 0 to 1. The derivative range is a probabilistic, and the key issue is overconfidence, and it is mainly suitable for the multi-class classification problems. So here we discussed mainly what is an activation function, that is, what is an activation function in deep neural network, and what are the key roles of activation function, that is how it controls the firing of neurons, and how it enables the deep learning model to learn the complex patterns. And then we discussed the types of activation functions, like we discussed a step function, sigmoid function, ReLU, tan h, and then we discussed how to choose the best or the suitable activation function. So thank you for watching this video.